Welcome to The Explainer. Today, we're doing some historical detective work, but on a cosmic scale. We're going to wind the clock back 300 years to uncover the secret magnetic life of our very own star, the Sun.
But right away, that brings up a pretty huge question. Today, we've got these incredible satellites watching the sun 24/7, but how on earth can we see the invisible magnetic forces that were driving solar storms centuries ago, long before any of that tech existed? Where would you even start looking?
All right, so here's our game plan for this amazing scientific journey. First, we'll tackle the mystery itself. Then, we'll hunt for clues hidden in old sunspot records. We'll see how scientists cracked the code of their behavior, how they rebuilt the sun's past, and finally, what this incredible history lesson actually tells us. Okay, first up, the 300-year solar mystery. And this isn't just some academic puzzle. Looking into the sun's past is absolutely crucial for understanding its future, and that has a direct impact on us right here on Earth, from our power grids to studies about our climate. Here's the thing. Our really detailed, direct records of the sun's magnetic field, they're incredibly recent. Before the space age, there's just this enormous blind spot, a 300-year gap, where the magnetic data, well, it just doesn't exist. So what did astronomers even have to work with?
Well, the answer lies in the only long-term solar data we've got: simple drawings and counts of dark spots on the sun's surface. These were meticulously recorded by astronomers for centuries, and these sunspots, there are historical breadcrumbs.
For hundreds of years, astronomers noticed that sunspots aren't just random. Nope, they follow a steady, predictable rhythm. The number of spots rises and falls over about 11 years. You can think of it as the sun's heartbeat, its fundamental sunspot cycle, and it's all driven by magnetic activity. But what's really fascinating is where these spots show up. At the start of a new cycle, they pop up in the sun's mid-latitudes. But as the cycle moves along, new spots start emerging closer and closer to the equator. And when you plot this whole migration over time, it creates this beautiful and frankly famous pattern, the butterfly diagram. So here's the puzzle. From most of history, we only have records of the number of sunspots, not their exact location or their size or their magnetic properties. To fill in that 300-year gap, scientists had to find a way to decode their behavior. They had to find the hidden rules of the solar cycle.
And their idea was pretty brilliant. They looked at a specific period, from 1874 to 1976, where we have it all. In those years, we have the simple, historical sunspot counts and the detailed scientific measurements from observatories. They use this overlap to hunt for statistical patterns that connect the sheer number of spots to their actual physical properties.
And you know what? They found them. They discovered a whole set of clear rules. First, stronger cycles, the ones with way more sunspots, tend to start at higher latitudes on the sun. Second, the sunspots are, on average, just plain bigger during a cycle's peak. And third, get this, even the magnetic tilt of sunspot pairs is connected to the cycle's strength. They had basically cracked the code. This quote from the research paper just sums it up perfectly. With these new rules in hand, scientists could take those simple sunspot counts from the 1700s and work backward, creating a statistically robust reconstruction of where those sunspots likely were, how big they were, and even their magnetic tilt.
Okay, so now they had a really detailed list of what past sunspots were probably like. But that's not the same thing as a full magnetic map of the sun, right? For that, they needed to turn all that data into a virtual time machine.
And here it is. They used a super sophisticated computer model called a surface flux transport model. You feed it all that reconstructed sunspot data, which basically tells it where and when magnetic energy pops up. And then the model uses the laws of physics to figure out how those magnetic fields would have spread and evolved across the entire sun's surface over time. But how do you know if your time machine is even accurate? Well, you test it on a period where you already know the answer. So here, you can see the model's reconstruction for a modern period compared against real observations. And the result? It's an incredibly close match. That gave the scientists huge confidence that the model's trip back to the 1700s would also be reliable. And this, right here, is the ultimate visual proof. On one side, you have the real butterfly diagram, built from decades of direct observation. On the other side, the diagram their model generated completely from scratch, just using those old numbers. The patterns, they're nearly identical. The time machine was working. Okay, so what did we actually learn from this incredible 300-year reconstruction? This is the big payoff. This is where the model stops being just a cool simulation and becomes a tool that can answer scientific questions that are centuries old.
One of the biggest discoveries is a game changer for solar forecasting. The model confirmed that the magnetic field at the sun's poles acts as a kind of memory. The strength of that polar field at the end of one 11-year cycle is a really powerful predictor for how strong the next cycle is going to be. This gives us a real physical basis for predicting future solar activity.
And now for the climax of our detective story. For decades, there's been this debate about an unusually long, quiet period in the 1790s. Some astronomers argued that early observers just missed an entire, probably weak solar cycle. So, could the model finally settle the case of the lost cycle?
They decided to test the hypothesis head on. They ran their entire 300-year simulation 2 different ways. Think of it like an A/B test for history. The first run used the standard official record. The second run inserted that theoretical lost cycle right into the timeline and recalculated everything. And the result was decisive. Okay, so when the sun is more active, it actually shields Earth from cosmic rays. These cosmic rays create a specific isotope, beryllium-10, which gets trapped in polar ice, creating a physical record. The model with the lost cycle predicted a timeline for these beryllium-10 levels that was off by 15 years compared to the actual data from the ice cores. The model without it, though, a good match.
So the big takeaway here is that this virtual time machine gave us powerful evidence to solve a historical mystery. That lost cycle? Yeah, it almost certainly never happened. The long, quiet period in the 1790s was just, well, a long, quiet period. And this just leaves us with a final, fascinating thought. This entire reconstruction of 300 years of solar magnetism started with nothing more than simple counts of dark spots on paper. It really makes you wonder, right? What other profound secrets about our universe are just waiting to be unlocked, hidden away in history's forgotten data?